Hi, my name is Brendan Colbert, and today I'll be talking about a convex optimization approach that can be used to improve suboptimal hyperparameters of sliced normals. We use sliced normals to characterize complex data-generating mechanisms, or DGMs. We assume that each DGM has some underlying probability density function, or PDF, that describes how the data, delta, are drawn. For a control system's perspective, each delta I could represent the coefficients of an uncertain plant model that we wish to characterize. Now we can directly model the DGM by modeling the PDF as a sliced normal PDF, or we can find the level sets of our sliced normal PDF, which are polynomial inequalities that tightly enclose the data. Here we have two DGMs that have areas where delta is drawn with a high density and areas where delta is drawn at a little or no density. We can use sliced normal PDFs to characterize the density of the points, where the red areas are in high density and the darker blue areas are areas of little to no density. We see that despite these two DGMs being very different, we can still use sliced normals to characterize both of them. The definition of a sliced normal PDF is that it is an exponential function of a sum of squares polynomial, phi, that has been normalized, as can be seen in equation 1. The sum of squares polynomial phi is determined by the hyperparameters mu and p, and is of degree d, where the user selects the degree of the polynomial. If the user selects a degree equal to 1, then f is just a normal PDF. However, for all degrees d greater than 1, sliced normal PDFs can characterize complex multimodal distributions that can characterize data such as those shown in the previous slide. Our question then is, how can one optimize mu and p given a dataset d in a user-selected degree? We select optimal hyperparameters that maximize the likelihood of the data d. The likelihood of the data d, shown here, is the product of our sliced normal distribution f evaluated at each of the points delta I within d. If LF of d is greater than or equal to LG of d, then that would imply that f is more likely to have generated the data d than the probability distribution g. For a given data set and degree, we want to be able to solve then for mu star and p star that maximize the likelihood of the data. In the case of a normal PDF, when d equals 1, there are analytical solutions for mu star and p star that can be calculated in O(n) cubed very efficiently, where n is the dimension of delta. Now, our prior work for optimizing the hyperparameters of sliced normal PDFs actually functioned by optimizing a normal PDF in what we call a lifted space. If our original dataset d consists of data points delta I, then we're going to define a lifted set of data, dz, which consists of the monomials of the data delta I. With these two data sequences defined, we have the following equality: that the likelihood of our sliced normal PDF is equal to a ratio of normalization constants, where the denominator is non-convex with respect to mu and p, times what we call the lifted likelihood, which is the likelihood of a normal PDF in the lifted space or with the lifted data in dz. This portion is convex because we have an analytical solution for normal PDFs. Therefore, the prior method worked by optimizing the convex portion of the likelihood, which is the lifted likelihood, and has an analytical solution where mu star is the mean of the data in the lifted space, and p star is the inverse covariance matrix of the data in the lifted space. While these hyperparameters are suboptimal, that is, by solving the true optimization problem, we may find the likelihood of the data that is larger than this suboptimal hyperparameters. We find that it works rather well and can be computed extremely efficiently. For instance, compare a sliced normal of degree 2 to a normal PDF on this data set denoted by the red crosses. We see that the normal PDF has large values in areas where no data exists, which is clearly bad, whereas our slice normal has large values centered around where a majority of the data is. Clearly, this is a much better fit than a normal PDF, even though these parameters are suboptimal compared to the normal PDF's optimal parameters. To visualize this, we'll consider a simple one-dimensional example. Here we have red crosses in delta, and we will lift this to a higher dimensional space where delta is on the x-axis and y-axis is delta squared. Once we lift this to a higher dimensional space on the left side of the video, we will optimize a mu star and p star of an optimal normal PDF in this lifted space. So here we see the data being lifted. We are optimizing a normal PDF, and then on the right we will plot the PDF in the original space, which exists on a slice of the normal PDF in the lifted space. However, this method does not always work. For example, consider the data that forms a figure 8 type shape in the upper right-hand corner. Using this prior method, if we fit mu star and p star in the lifted space, we find that the best likelihood of the data occurs with the degree 3 slice normal. This is unexpected since higher degree slice normals have a larger number of hyperparameters, and thus we would expect a better fit to be possible in the higher degree slice normals. However, in a degree 6 slice normal, we see that areas with a low density are underrepresented and areas with a higher density are overrepresented by our degree 6 slice normal. We see how this affects the PDF when we try and sample from the slice normals. We see that there are no samples in the low density areas of our degree 6 slice normals, whereas for the degree 3 slice normal, optimized using our prior method, we see a small number of samples in a lower density region, but we still don't see very good performance. Where we do see good performance as the degree of the slice normal increases is in the area of the minimal set that contains all of the points of our DGM. The degree 6 slice normal, for instance, these sets have much smaller area than the degree 3 slice normal sets up here. Now, this leads us to believe that if we rescale the polynomial argument in our slice normal, that we may be able to redistribute some of the density of our PDF to better represent these lower density areas. To do this, we will rescale the p star hyperparameter, but we will do so by optimizing the true likelihood. So here we have our normalization constant that is non-convex with respect to mu star and p star, but we see that it will be convex with respect to gamma. Therefore, we can optimize this problem using convex optimization and find a globally optimal gamma that rescales our p star matrix. Now, if we compare this new method, which is really just a second step on our prior method, we get the following inequalities. Of course, our non-convex solution, if we could find the globally optimal mu and p, is going to be better than our prior work, which is suboptimal. However, this work uses gamma to sort of close the gap between the non-convex method and our prior work, and the likelihood of the data will be greater than our prior work for this second step, but still may be less than the non-convex method. To solve optimization problem 3, however, we need to calculate the normalization constant. We will calculate the normalization constant using Monte Carlo integration by sampling uniformly over delta, the support of our slice normal PDF, and we can then estimate the integration constant as the average of our slice normal PDF evaluated at each of the samples SI, assuming that our normalization constant is 1. The error of the Monte Carlo integration is going to decrease as 1 over the square root of ms, which is the number of samples. and this will be independent of the dimension of the integral. Even with millions of samples, we can calculate the normalization constant relatively quickly, and the only thing that must be taken into account is that MS must be large enough to have accurate solutions. If we take the log of the likelihood of the objective function, which is our likelihood of the data, we find the following optimization problem, which is convex with respect to gamma, which means we can find the globally optimal rescaling factor. While this is convex with respect to gamma, it is still nonlinear, so we can use a program such as MATLAB's fmincon to optimize gamma. The resulting slice normal then uses the prior solution of U star and P star, but rescales P star using gamma star. And of course, we can recalculate our normalization constant. Doing this second step to rescale the P star matrix significantly improves our solutions. Here we see that our degree 6 slice normal now adequately models the lower density areas and still has very good modeling of the high density areas as well. When we resample this, we see that we get much better samples in the lower density regions, and we are not oversampling the higher density regions at the top and bottom of the data anymore. Now we see that, in fact, our sample data looks very similar to the data that was drawn from the DGM. The level sets are going to be the same since our sum of squares polynomial was merely rescaled. But that's okay because we actually saw good performance in the level sets of our slice normal PDFs as the degree increased. If we directly compare our prior work on the top to our new work on the bottom, we see that our new work provides much better sampling. The PDF appears to model lower density areas significantly better, and the level sets remain the same. For this data set in particular, our method has a 69.6% increase in the likelihood of the data between the degree 6 slice normal using the prior method and updating it with our new method using the convex optimization problem. In addition, we can sample higher dimensional distributions. On the left, we see data that has strong parameter dependencies that are clearly non-normal. Using a degree 4 slice normal, we can find these samples that look very similar to the data drawn from the DGM. Again, this process makes no assumptions on the underlying distribution of the data and only requires for the user to select a degree. Therefore, in conclusion, given data, delta I from I equals 1 to m, from a DGM of unknown structure, we can use slice normal PDFs to model the DGM by simulating new samples and finding polynomial inequalities that are level sets of our PDF that tightly enclose the data. The important properties of using this method are that we make no assumptions on the structure of the DGM, and that optimizing the hyperparameters can be done relatively efficiently since we have an analytical solution for mu star and p star, and solving for gamma star involves solving a convex optimization problem with only one scalar decision variable. That is regardless of the dimension of delta. In addition, now with our second method, we can increase the degree and the likelihood value of the data will generally increase as well. Thank you all for taking the time to listen to my talk.